So hello everyone, welcome back. And our first speaker for this session is Arkadev Chattopadhyay from TFR, and he is going to talk on monotone arithmetic lower bounds via communication or complexity. So it is yours. Yeah.
Okay, should I start?
Yeah, please.
Okay, thanks. Hi, welcome. Yeah, so this is some joint work with Rajit Datta, who is at CMI, and Partho Mukhopadhyay, also at CMI. So, yeah, so I keep seeing this problem of my screen not refreshing. Yeah, I mean, do you see the same problem as I'm seeing? Like there's the title has got chopped off.
Yes, actually, yeah, we are not able to see complete screen. The things are chopped up.
Yeah, so I don't know what to do.
There's a lot of blank space at the bottom of the page. Is it just some scrolling thing?
No. I don't think this is scrolling. I mean, because
Arkadev,
the full screen is.
I think it's slowly refreshing, and so previously I could not see the 78. Now I can see the 78 central questions. Now I can see the full title.
Oh yeah, now I can also see.
So it's very slowly refreshing.
Oh, that's very strange. Okay, yeah. Okay, so I will try, but I will probably have to speak a little quicker. Okay, so fine. So so these are the central questions that more or less everybody knows in Boolean complexity, where the objective is to compute Boolean functions. The main question, sort of the defining question of computational complexity, is this P versus NP question raised by Steve Cook in 1971, which basically asks, whether every function whose solution can be efficiently verified, whether we can find a solution also efficiently. And the analogous question, which will be the focus of this talk in the algebraic world, is Valiant's question, which was raised in 78 by Les Valiant, is the same question in the algebraic world, where we have two classes. So here, what we want to compute are polynomials. We have been doing a lot of polynomials in the last few talks. So we want to compute polynomials as formal objects. I'll define the model pretty soon, but you saw that in Prerna's talk, for instance. So we want to compute polynomials, and how efficiently can we compute them? That's the question. And analogous to NP, I don't want to go into the details. There is a way of defining similar thing called VNP in the algebraic world. These are polynomials again. I mean, in some sense, algebraically, you can express them as projections very efficiently. And the point is, can you compute these polynomials in polynomial size with what are called arithmetic circuits? So, yeah, as I said, this was Boolean function, and this is formal polynomials. So the reason, these are two very important questions. I mean, the algebraic complexity question is independently interesting in its own right. It's a very natural question, but there's another sort of hope, which is that after all, polynomials are much more structured objects, have been around and studied since ages. So potentially, more tools from classical mathematics should be available to resolve that question, the VP versus VNP question, as opposed to the P versus NP question. And so the hope is sort of that potentially this is a more tractable question than the Boolean complexity question. But unfortunately, both these questions remain wide open. We don't seem to have come any closer in the last few years. So let me, before I delve further into it, let me quickly remind you of the model. So our model here, so the screen is taking its own time to refresh. So the model here is that of arithmetic circuits, where Prerna already defined this, but there's a crucial difference between what she was talking about and what I'm going to talk about here. Is I'm going to deal with the simpler world of commutative models. So here all I have some underlying field and the variables commute with each other. It's the usual situation. And the natural model, if you think about for computing polynomials, is when you have gates which can sum and multiply. Okay, so you have a circuit with gates, which there are the sum gates and multiplication gates, and the input variables. So you want to compute some polynomial of the input variables. They are at the bottom, and they are fed into the circuit. And then there is a special gate called the output gate, at which you are expected to compute the polynomial. So, for instance, in this particular case, as you can see, is a simple polynomial x1 square minus x2 square that's being computed. And you can use arbitrary constant of the underlying field as part of your computation for free. And you can subtract by just putting a -1 on the edge connecting the one gate to the other, which means that the negation of the output of the gate which is feeding into the input into the next gate is what is fed in. Okay. So yeah, so this is simple to see. And what is important for us is to understand these two parameters of a circuit called the depth and the size. So the depth of this circuit is 2. The length of the longest path in the underlying graph is 2 from root to leaf. And the size, there are 3 gates. So by size, I would always mean in this talk, the total number of gates that are being used. The size is 3 because there are 3 gates being used. And in this talk, although arithmetic circuits can be defined over arbitrary fields, this field I'm going to fix for now is the field of real numbers. This whole talk will be about real numbers. So first thing to see, just to quickly be on the same page, is that this is a universal model. After all, every object of interest, that is namely polynomial, can be computed by some circuit. Okay, because if you just express the polynomial as a sum of its monomials, then you can use a depth 2 circuit with a big fat plus gate at the top, and then feeding into those gates are all these product gates. Each product gate is computing a monomial, and what I've missed out here is this edge. You're sort of also feeding this constant. So I mean, what you can do is you can also multiply the constant into the product gate, which I've missed out. The constant being the coefficient of the monomial. So each product gate will also have that, and so this way you can certainly compute any polynomial in depth 2. So it is very much a universal model. It's a trivial observation, but it's good to know that. And the size, however, of this circuit could be very large. It is as large as the number of monomials of your polynomial, because we associated each monomial with a product. Okay? So at the depth 2 layer, the number of product gates will be exactly equal to the number of monomials. Okay, and the question we are interested in is, can you do things more efficiently? Now that we know that everybody has a particular circuit, the question is, how efficiently can you compute a polynomial? So let's take a quick example. This is the polynomial which is known as the elementary symmetric polynomial of degree d, right? So it's a multilinear polynomial. You're going through all subsets of n, where n is the number of variables, and you only look at sets of size exactly d. So thereby you get all the degree d multilinear monomials, very standard polynomial. And we know that by a depth 2 circuit, it can be computed by in size n choose d. Now, if d is large, like non-constant, this certainly is super polynomial size, super polynomial in n. Note, however, that in this circuit, I have not used any negation. No minus, no subtraction is taking place. The polynomial, all its coefficients are non-negative, and I am not using any negation in my circuit. You may ask the question, can you do any better? So, because in general, I would be allowed much more depth than depth 2. Okay. So the answer, the sort of surprising answer, if you haven't seen this before, is that you can do it in a lot better way just by increasing the depth by 1 in depth 3. Then you can compute it in size roughly about n square. Okay. However, it's a very counterintuitive way of computing this polynomial. Namely, you suddenly start using negative numbers all over the place. Okay, so you use the power of cancellations, and they are very powerful because at least in depth 2, with no cancellations, I required exponential size depending on how large my d was. But no matter what d is, I can always compute it in size order n square by just increasing the depth by 1 and using the magical power of cancellations. This is the famous theorem due to Benor. Okay, so the moral of the story is that cancellations can give you unusual or unexpected power. Okay, now let's look at another very common polynomial called the determinant. Now again, the determinant has, for you go through every permutation, the number of monomials. So now the variables of my polynomial is, you can view them as sort of associated with a n by n matrix. Each entry is a formal variable. Okay, and you all know the determinant polynomial. So it has got now both negative and positive signs because the sign of the permutation comes in with the monomial. So it's got plus 1 or minus 1 coefficient. And again, you can compute it in depth 2. But you will require very large size, factorial n, the size of the symmetric group, the number of permutations. And you may again ask the question, is this the best that you can hope for? And again, the surprising answer is, well, with a lot more depth than constant depth, if you allow yourself depth log square n, now this is depth which is increasing as n increases. So for every n, I've got a circuit of that much depth log square, still much smaller than what you would have thought, but in depth log square n and size polynomial in n, you can compute the determinant. Okay, so you can again, and this I would say uses even more fancy calculations. Cancellations. Okay, I will say what I mean by more fancy than before in a while. So and therefore again, if you allow cancellations, you can compute things in much more non-obvious ways and be more efficient. Finally, let's look at the close sibling of the determinant called the permanent, where it's exactly the same polynomial, again defined on n square variables, degree n, where we just forget the sign of the permutation. So all coefficients are 1. Okay, there's no negative number involved. So this is a polynomial with all non-negative coefficients. And again, the question is, what's the best way to compute it? Can this be computed in polynomial size? And this is, if you haven't seen this before, this is sort of surprising that, although the determinant has such a nice polysize circuit, here the question is wide open, and it's widely believed that even with cancellations, no polysize circuit is possible. In fact, just as you have NP completeness, there's a notion of VNP completeness that one can invoke or define, as Valiant did, and this is a VNP complete problem. So, this is one of the cardinal targets of proving lower bounds. We do not expect the permanent to have polysize circuit. Okay? And in fact, you can show that if you tied the circuit's hands behind, meaning you didn't allow any negations in the circuit, then in fact you would require exponential size. Okay, so without cancellations, provably this requires exponential size, but with cancellations, again, we do not expect in this particular case cancellations to help, but we cannot show any good lower bound. So this is the state of affairs. And now I want to come to the topic of this talk, which is basically about monotone computations of monotone polynomials. So the permanent that we just saw is an example of a monotone polynomial, which means that the polynomial, all the coefficients, all the coefficients of the monomials of the polynomial are non-negative. There's no negative number there. Okay, such a polynomial is a monotone polynomial, and it's seems natural to expect that maybe, whenever a polynomial is monotone, I mean, you don't even need the notion of negative numbers to define these polynomials. Why should cancellations help? Maybe cancellations should not help, right, to compute these polynomials, which are monotone. Okay, and so we define circuits which are monotone circuits where we do not allow any subtraction or cancellation. Okay, so these are circuits where no negative numbers are involved. And this defines the class of monotone VP, which is all monotone polynomials that have polysize monotone circuits. Okay. Now, we have had great success in proving lower bounds against this model. As I just told you, the permanent, when you tie the hands of a circuit and insist that the circuit cannot use any cancellations, then one can show exponential lower bounds, for example, on the permanent. And this was shown very early on by Shamir and Sneer from 1979. Okay. And this, in fact, the argument is a very simple combinatorial argument. It's not a very difficult argument. It's still a very interesting argument. Now, in the Boolean world, you can ask the same question, right? You can make your circuits monotone, and you can take a monotone function like click, where now you're given a graph. The input is the edges of a certain graph, and you're asked whether this graph, the Boolean question, whether this graph has a click of a certain size. Now, that's a monotone problem in the sense that if I add edges to my graph, a click that was present cannot go away. If there was a click present, it would continue to be present as long as I keep adding edges. Okay, it is monotone in this sense. And to prove this result, that click is not in monotone P, so there are no monotone efficient computation of click, of years later than the Shamir-Sneer result, and it's way more delicate combinatorially, reinforcing this intuition that one has, that when you try to prove results on Boolean complexity, they are much more difficult to come by. Okay. And we have had many other success, both in the Boolean world and in the arithmetic world, for proving lower bounds against monotone computation. But a certain question that we want to understand in this talk is, what exactly is the power of negation or cancellation? Well, it seems that, if as I said, for permanent, if I allow circuits to use cancellation, then I'm not able to prove lower bounds. Is there a good reason for that? Right? So how helpful is negation? And this question, again, can be asked both in the Boolean context and in the algebraic context. Okay? And in both cases, we know that indeed, I'm just reminding you, we know indeed that there can be a lot of power gained by allowing cancellations. So in the Boolean world, Razborov showed in 85 that the perfect matching function, so I give you a bipartite graph and I ask you whether this has a perfect matching. This, of course, is in polynomial time. This is an algorithm that we learned in an algorithm class. And Razborov showed very interestingly that this is not in monotone. So matching, again, if you have a perfect matching, if you add edges to the graph, it will continue to have a perfect matching. It's a monotone function, but strangely, the power of cancellation is crucial to compute it efficiently. Now, again, matching features in the algebraic answer as well. So if you look at what are called matching polynomials, so what do I mean by a matching polynomial? I'll just give you a brief overview. So for if I give you a graph and there is a matching polynomial of that graph, so this polynomial is associated with every edge of this graph, there is a variable, okay? And I only consider multilinear monomials. So each multilinear monomial naturally encodes a subset of edges that I give you. And this monomial will be present with the coefficient 1 if this corresponds to a perfect matching. So if my graph is a planar graph and I look at the matching polynomial of this planar graph, okay, you can show that this can be efficiently computed. This polynomial is non-negative, so it's a monotone. All its coefficients are non-negative, so it's a monotone polynomial. But if the graph is planar, then using the computation of determinant, you can actually show that this can be efficiently computed. So it uses cancellation. And Valiant, again, 6 years before Razborov's work, showed that for a certain carefully chosen planar graph, the corresponding matching polynomial cannot be efficiently computed with monotone circuits. Okay, thereby again showing in the arithmetic context that this was the first result by Valiant, which showed that negations are provably exponentially more powerful than monotone computations. So, I mean, well, we could say that we have understood everything that we need to understand about the power of negations. What more is there to understand? Okay, so sort of a mystery that has not yet been resolved is the following, which is that, okay, I can take this question to the extreme setting, right? I can look for the simplest model of general computation. By general computation, I mean computation that allows cancellation. Let me look at the simplest model. And can I show that the simplest, there is some monotone function or monotone polynomial, depending on what context, the arithmetic or Boolean, such that in the simplest model of computation with cancellations, there is an efficient circuit, but in the most powerful model with cancellations, there is no efficient circuit. Okay, this is the question that we would like to ask. What do we know about that? How does the matching result fit in with this question? We know that matching is not in monotone P. It cannot be computed efficiently. But matching is not known to be computed, let's say, by circuits of constant depth. Okay. In fact, Raz and Wigderson showed that matching, if you only look at formulas, not even circuits. So these you might think of even as circuits of small depth, meaning circuits which can compute in fast parallel time. Okay. So Raz and Wigderson showed that in order to compute matching fast in parallel, it's not possible. Okay. This was the result of Raz and Wigderson, and the latest answer from work from 2 years back due to Gus and others shows that there is a function which can be computed by circuits using cancellations in really fast parallel time, like in what complexity theory is called NC2, which is depth log square n. Okay. However, to compute it using monotone circuits, you still require exponential size. So here's an example of a function which improves on the Razborov result, right? You found out a simpler model of computation, namely depth log square n. Even there, this function can be computed efficiently using cancellations. But in the strongest model of monotone computation, you still require exponential size. Okay?
Arkadev, I have a question.
Sure.
Yeah, so this Raz-Wigderson result is against monotone formulas or not monotone?
Yes, monotone formulas. That's
okay. Thank you.
Yeah. So we don't know whether matching can be computed by general formulas efficiently.
Okay.
I mean, like let's say log depth.
Yeah. Okay.
Yeah. So okay. So now, what happens in the algebraic world? Well, in the algebraic world, actually, Valiant's result was, in some sense, the best result. We didn't have improvements over that, in the sense that there was really no monotone polynomial one had, which could be computed with general circuits much more efficiently, let's say in very fast parallel time. There was no such polynomial known. There was another result due to Jerem and Sneer, which was about spanning tree polynomials, but its complexity is similar to that of the matching the matching polynomial. So the The most extreme form of that this question can take is this following, which is that can you find functions or polynomials which can be computed by constant depth circuits? Okay, so these are circuits where the gates have sort of large fan-in. You allow arbitrary polynomially many inputs to feed into each gate. Otherwise, constant depth doesn't make sense. So these are extremely small depth circuits. Yeah, the depth doesn't change with n, the number of variables. So in these kind of very shallow circuits, can you find a function or a polynomial which can be very efficiently computed with cancellations? But unrestricted monotone circuits do not help you. You still require exponential size. This, I think, is a very interesting question. It has been very intensively looked at in the Boolean world. There had been attempts also to answer this question in the arithmetic world, in the algebraic world. So in the Boolean complexity world, this is still open, wide open. And in the algebraic complexity, this was open until our work. And there was one work a few years back due to Pavel Rubish and Amir Yehudayov, who showed in the model that Prerna was earlier talking about, in the non-commutative model, they actually answered this question in the positive, meaning they showed that there is a polynomial in the non-commutative polynomial, which can be computed in constant depth with using cancellations. However, in the monotone world, unrestricted circuits require exponential size, but they could show it only for the non-commutative world. And as you can imagine, the non-commutative world, the power of cancellations is sort of far more limited than in the commutative world. So for the commutative world, this question was still open, and this is the main result that we are going to talk about here. We answer this question in the positive. We resolve this question for the commutative world. Any question? Okay, so our main theorem is the following. So there exists some polynomial in n variables. Now I have changed to capital N. Sorry about that. And the degree of this polynomial, so it's a monotone polynomial. Okay, so it has all non-negative coefficients, and the degree of this polynomial is about square root of n, such that P can be computed by a depth 3 formula or a circuit of size barely over quadratic. Okay, so but the monotone complexity of this polynomial with unrestricted depth is still exponential. This answers exactly the question that I had asked in the context of arithmetic circuits. So that's our main result. And one remark about it is that this result is optimal. In what sense is it optimal? It's optimal in the following sense that, as I said, our polynomial can be computed by a depth 3 circuit or even formula. Depth 2 circuits, you may want to ask, what about depth 2 circuits? So depth 2 circuits, you cannot expect such a thing, because depth 2 circuits, if you think about it, they cannot exploit cancellation. What I mean by that is, if there is a monotone polynomial that is computed by depth 2 circuit general circuits efficiently, then there is also basically a depth 2 monotone circuit that can compute it. Because if you look at a sigma pi circuit, essentially you will be just computing it monomial by monomial. So in depth 2 you cannot hope to have any interesting power of cancellation. But as soon as you go to depth 3, what our result shows is there's huge power of cancellation. So in this sense, our result is optimal. Any question?
Arkadev, so what is the monotone complexity upper bound for the polynomial you consider?
So I think it is by depth 3 thing to the square root of it, instead of n to the 1/4 of the square root of it.
Okay, yeah, thank you.
So yeah, so our lower bound in that sense is not optimal even for this polynomial. It is possible that square root of n is in the exponent is the right one. Thanks. Okay, so in the rest of the talk, what I'm going to focus on, I'm going to mainly focus on, how do you find this polynomial? This polynomial comes from a strange source, at least a source that is not very common, I believe, in arithmetic circuits. Okay, how do you find such a polynomial? And then, of course, there's a question about, well, once you find this polynomial and show that there is an upper bound, you have to, of course, do the lower bound. And how do you prove that lower bound? Now, a communication complexity has been sort of used to prove lower bounds in arithmetic circuits, in the sense that there has been intuition. There's been no direct connection, except for the work of Raz and Yehuda a few years back. But otherwise, there have been not sort of lower bounds have not been in some sense ported from communication complexity to the arithmetic world. But people have drawn intuition from there. What is more interesting and somewhat surprising, at least for me, is that this polynomial that we find comes from the connection to this famous log rank conjecture in communication complexity. So we were guided to look for this polynomial by the log rank conjecture. Okay, this is the to me the most surprising and perhaps the most illuminating part. And in the rest of the talk, I will basically most of it will be spent in sort of a story towards how do we find out this polynomial. I would like to share with you how we found out this polynomial. And there is another lower bound which I will not. It's a somewhat technical result. In a certain for those who are interested, I can talk offline. But there's a certain very interesting program that Pavel Rubish came up with, which said that in some sense proving monotone circuit lower bounds is enough if you prove it for a certain kind of monotone functions to prove general lower bounds. Such a result, of course, is also known in the arithmetic world since ages, the slice functions. Okay, but in the context of arithmetic circuits, this was new. And he suggested this program a couple of years ago. And the ideas we sort of that went into proving our first lower bound, we saw that those same ideas can be extended to prove, to take the first steps sort of in this program as advocated by Rubish. But beyond this, I won't talk about this. So if you want to know more about that, I can talk about it offline. Okay. So how do we find out this polynomial? Let's again quickly review what kind of power of cancellations do we know? Yeah, when do we know cancellations help? As I said, the primary object in the arithmetic world, the primary polynomial whose computation involves cancellation is the determinant. This, in some sense, is the most fancy cancellation that happens because while computing the determinant efficiently, a determinant is a multilinear polynomial, right? You start generating monomials that have no meaning, that do not even occur in the determinant. Okay, and then by magic, those monomials completely cancel out. This is what I'm calling non-multilinear cancellations. This is a very powerful form of cancellations. And so those cancellations help you compute a function like the determinant. And there are many, many algorithms known there. But, these are, I mean, so far we don't know how to carry out such powerful cancellations in constant depth, even in like depth log of it. And we do not expect such cancellations, in fact, to be possible in shallower depth. So, of course, such cancellations, therefore, would not be of any use for us if we want to find a polynomial in constant depth. Then the next thing is another powerful cancellation that I alluded to before due to Benor, which is interpolation. Here, the cancellation I say is less fancy because the cancellations are still, you're computing a multilinear polynomial and you do multilinear cancellations. Okay, so in that sense, this is less fancy. And this can be carried out in constant depth. This can be carried out in depth 3. And it can compute the elementary symmetric polynomials. So one question is whether why not take the elementary symmetric polynomials? We saw that if you want to compute monomial by monomial, in one of my earlier slides, I showed you that this will require exponential size, right? So an elementary symmetric polynomial could have been a good candidate. Unfortunately, what happens is, there is a very efficient monotone circuit that computes it in much, not constant depth, but larger depth. And therefore, this kind of cancellation using interpolation also doesn't seem useful for our purpose. Yeah, it's so far interpolation has not been able to give us this kind of polynomial. So it turned out that we needed to explore some new powers of cancellation. And as I said, in depth 2 circuits, there's no question, right? So the first thing to look for is depth 3. Yeah? And if you look at depth 3, and if you hope there's cancellation, the best hope is for random depth 3 circuits, right? When you give random negative numbers and positive numbers, and I'll make it formal what I mean by that, I mean, you expect a lot of things should cancel, right? So let's look at a random depth 3 set multilinear circuit, and I will, this is some fancy name, but you will see what I mean by that. This is like the simplest kind of circuit, because we want to look at this, we want to look at simple circuits. Okay, so what do I mean by set multilinear circuits? So this is very similar to what Prerna was talking about. I mean, she also had these blocks and so on, and except that in our case, everything commutes. It's the commutative model. So I have n blocks. My variables, there are some number of variables which I've divided them into blocks. There are n blocks. Each block has m variables, m for mother, right? And I want to compute a function of these variables. Okay. So let's look at a depth 2 circuit, a random depth 2 circuit. Okay. So a random depth 2 circuit will be a product gate at the top and then some gates at the bottom. Okay. And this product gate is going to be n-fold. And what I'm doing, each of these sum gates at the bottom, it's computing a sum of a particular block. The coefficient of the variables in the block are being chosen at random, either 1 or -1. These BIs are bits, 1 or -1, or rather, sorry, numbers 1 or -1. They're chosen independently at random. So there are m variables per block. And so you have to choose m of these numbers, 1, -1, totally at random. Probability 1, half, 1, and half -1. Okay, but you just choose m of these. And then you use the same B1 to Bm for every block. B1 goes with the first variable of the first block. B1 also goes with the first variable of the second block in the second sum gate, and so on. Okay, so is this clear? Yeah. So you just take a sum weighted by this B1 to Bm for all the, block after block, and then just take a product. So that's a depth 2 circuit. That's a random. This is what I mean by a random depth 2 circuit. The only source of randomness here is the B1 to Bm, right? So you sort of flipped m bits. Okay, and then you can make up a random depth 3 circuit in a natural way. Given a way to build random depth 2 circuit, all you do is you choose such random depth 2 circuits independently at random a few number of times, and then sum it up. Sum each of these random depth 2 circuits together. Yeah, and you sort of normalize it. So capital N is the number of such depth 2 circuits that I chose at random, and then I'm sort of summing them. That's all. Okay. Now let's understand what's going on here. What sort of cancellations are occurring here? Okay. Oh, so just to say this. So now, since I've chosen, capital N many such random depth 2 circuits, each random depth 2 circuit got its own copy of this B, which I'm with a superscript I'm representing, right? B superscript 1 is m random numbers from 1. M random numbers all either 1 or -1 for the first circuit, B2 is for the second circuit, fresh copy, and so on. Okay. So let's look at the pattern of cancellation. So let's look at a monomial. So by what do I mean by the pattern of cancellations? I want to understand what the coefficients of these monomials will look like. Yeah, what kind of things are happening. Now notice, since I mean, each of these depth 2 circuits, what were they doing? They were just taking the product of a sum, blockwise sum, right? So this, when you look at a monomial that is being generated by such a product, right? Every monomial naturally is associated with a map, right? The map is from the block to which variable on the block that you chose, right? That map is being called sigma. It's not a permutation, it's a map. Yeah? In fact, M and N are different, okay? And so a map defines a set multilinear monomial, and a set multilinear monomial defines a map. So that's all, right? Okay. So what we would want to understand is the coefficient of such a monomial in this sum. Okay. And it's simple to observe that the coefficient of a particular monomial given by the map sigma, yeah, for the ith subcircuit would be exactly this, right? The product of those coefficients. Yeah, because you chose the from the first block sigma 1th copy, so you look at the sigma 1th b of from the first block, right? And so on, right? And you take the product of these things. So this is exactly going to be the coefficient of the monomial that the ith depth 2 subcircuit will contribute. Okay, and therefore you just need to sum them up, right? I mean, so we want to understand what this product is. So now this product can be re-expressed in the following way. Yeah? I mean, look at L. It is some number from 1 through M. Now BL, the Lth copy of BI, how many times will it occur? Well, as many times L was hit by the map sigma, right? And that's all I've just said. Yeah. But notice these numbers are from each BIL is 1 or -1. So all that matters is basically the parity of this numbers, exponents, right? So I can replace it by mod p. Okay. Yeah. So this is exactly the coefficient. Each coefficient is 1 or -1, and this is what gives you the 1 or -1. So far, so good. And this motivates us to define what is called the parity vector of a monomial, right? And this is going to be a crucial concept. Okay, so the coefficient of a monomial in this sum, in this random sum, is going to be exactly the sum of the coefficients contributed by each of the subcircuit. Yeah, so which you are given by this mod 2 thing. Yeah, so this is not refreshing very fast. Yeah, and therefore, if I know the parity vector, right? All I need to understand this coefficient is basically the parity. This is what I mean by the parity vector. Okay, so because if I know the parity vector, which is given by the following things, meaning it's an m-dimensional vector corresponding to each of the copies. I mean, each of the block, each block has m size m is the same m, and basically it's just saying the sigma inverse of 1 is saying how many times sigma hit 1, mod 2 was it odd or even, and so this vector is just a 0, 1 vector, right? It's an m-dimensional binary vector, and this vector completely therefore determines the coefficient of this monomial kappa, right, in our sum. Nothing else matters. This is simple observation. This is just exactly how things are working out, and therefore, if I chose randomly my sum, then what is going to happen is, if my parity vector, if each of these things, if the parity vector was all zeros, meaning each of these things was hit even number of times, then every random circuit, subcircuit, depth to subcircuit contributed 1, and I've then normalized it by 1 over n. So the coefficient, there's no cancellation, right? You get the coefficient 1. There was absolutely no cancellation. However, if your kappa had even one sigma in, one of these things being hit an odd number of times, yeah. So if any in the parity vector, if you had even one of the positions as 1, meaning odd, right? Then in expectation, the whole thing, the expected sum, the expected coefficient will be 0. Another way to think about it is like if I chose, if I chose all these depth 2 subcircuits that I could have chosen, forget about randomness. If I chose all the depth 2 subcircuits, then there would be perfect cancellation, and this whole thing would cancel out to 0, right? So if I chose everything, then then things would perfectly cancel out, and then this would be 0. But then that would be too expensive because I would have to choose many depth 2 subcircuits, right? And we can simulate these things by, that would be too expensive. So, I would replace this by a judicious choice of a certain pseudorandom object. These are called epsilon, for example, epsilon bias spaces. Yeah, you can choose these epsilon bias spaces such that, your sum, B1 to Bn, this coefficient vectors, if they come from an epsilon bias space, this is not too large, still the sum would be very close to 0. Yeah, you can make your sum as close to 0 and not blow up by too much, right? So the point is the cancellations are happening in such a way that the only thing over which cancellations are not happening is the monomial, which corresponds to the parity vector being all 0, and everything else is cancelling enormously. So how do we exploit this? So this gives rise to a general framework for constructing polynomials.
Arkadev, a quick question. So
Yes.
the polynomial as described could potentially have negative coefficients also.
That's right. That's right. So far, you're right. Absolutely.
Okay. Okay.
Right. Yeah. So far, I have not told you how to make it this, but there's a simple trick. Since you asked me, let me just say, and I'm running short of time. So yeah. So you see, because this will be one of the coefficient will be exactly 1. The other could be minus epsilon to plus epsilon. Right. Now you can sort of subtract it from the full polynomial with all 1 coefficients, and then everything would become positive. Right. So then the one which had all 1, it will become 0. It will completely disappear, and the other ones would become positive, very close to 1. Right. So this is not a big problem. Okay. And that subtraction is sort of one subtraction. It's easy to do in depth 3. Okay. So in fact, that's what we will do. But more generally, this is something I want to highlight, is that this is a nice way. Now we can create, monotone polynomials in the arithmetic world by looking at the Boolean world. So I look at a Boolean function f, on m variables, and every such Boolean function will give rise to a monotone set multilinear polynomial in the following way. Well, so it's set multilinear. So all non-set multilinear monomials will not appear, will be 0, and every set multilinear monomial will have a value either 0 or 1 by just evaluating f on its parity vector, the same parity vector that we used for cancellations, right? And this, we feel, is a very powerful way to sort of build a correspondence between the Boolean world. You can now start looking at combinatorial parameters of the Boolean function f and say things about the monotone arithmetic complexity of P of f. Okay, so this is the interesting thing. It's a very simple construction, but it turns out to be very useful. Okay, and I have 5 more minutes, right? At least.
Yes, yes.
Yeah. Okay. So, yeah. So let me just tell you.
9 minutes. Yeah.
Oh, I have 9 minutes. Oh, great.
Yeah.
Sorry. Yeah. Okay. So I have still not come to the log rank thing, and I want to show you that. So now, what is it that we need from our Boolean function f? At one end, we need this Boolean function to be such that, polynomial induced by this Boolean function is computable efficiently by depth 3 circuits. And the sort of competing other requirement is that it should still need exponential size to be computed by unrestricted monotone circuits. Okay, so let's first see that, what is our constraint? If we want it to be easy for depth 3, it will turn out that in a certain sense, its rank has to be small, the algebraic rank. What do I mean by that? Let's look at it carefully. So we've got this P of F. Yeah, so any polynomial, for that matter, it's a set multilinear polynomial and it has a depth 3 circuit, right? So in fact, it has a depth 3 set multilinear circuit. So it can be expressed as a sum of products, and each of these products is a product of linear forms. Each one is over the block variables. Okay, and now if you take any partition of your blocks, there are n blocks, choose any partition of those blocks into 2 parts, A and B. And now, much like what Prerna was saying earlier, look at the following matrix, a natural matrix associated with this. This has been looked before as well. So A is a certain set of blocks, B is a certain set of blocks. My rows of my matrix, they correspond to set multilinear monomials that come from block A. And the columns are all monomials, set multilinear monomials that come from the variables of which are in block B, which are in B, all the blocks in B. Okay, and so MA and MB, the corresponding entry is just as, so it's a Boolean matrix, 0, 1 matrix, where you fill in with the coefficient of MA times MB in the polynomial P of F. It's a very natural matrix. And so this is this matrix. And now if you see this, just by the fact that, the depth 3 circuit has given you basically a rank 1 decomposition. So with respect to this AB partition, your rank is at most S. If there were S things used up in your sum, it's simple to observe that the rank of this matrix with respect to every possible partition is at most S. Okay. So you get low rank. This is what I mean by low rank. So easiness implies that your function must have low rank. That's a constraint. Okay, and on the other hand, I want to prove a monotone lower bound, and all monotone lower bounds, they're proven in the following way. So there's something called a structure theorem, which means that if I have a monotone circuit that computes my polynomial in size S, then the structure theorem says that this polynomial actually can be decomposed into a sum of product polynomials. Yeah? These product polynomials, so alpha I and beta I, these are simple polynomials, set multilinear polynomials whose product you're taking. So alpha I, bi is a product. And for the ith guy is alpha I, bi, corresponding to this ith guy, there's some alpha I depends on some of the blocks. So IA is a set of blocks that alpha I depends on. Here's IA. And IB is a set of blocks that beta I depends on. And this forms a partition. This is what the structure theorem says. And this forms it's a technical condition. It's sort of a balanced partition. Okay. But the important point is that, every alpha I, beta I comes with its own partition, in the sense that, if you move to the J, alpha J, Bj, the partition could very well change. But for a fixed partition, if you look at a fixed partition, again, alpha I, beta I, if you look at the same matrix that I was alluding to before, this is a rank 1 matrix. Okay. All in all, this means the following, that, it means that if I want to show that a certain, if I want to prove a lower bound by showing that this kind of decomposition, this kind of efficient decomposition is not possible, this would imply that the non-negative rank of my matrix you look at this polynomial P, you form a partition of its blocks. For every possible partition of the blocks, you can define rank, And it will turn out that for every balanced partition, the non-negative rank has to be at least S. Okay. So this is what the hardness, this would be implied. This is a weak implication. This is a necessary condition that your polynomial must satisfy if there's any hope to prove a lower bound. Okay. So the easiness condition says that your rank must be small, your ordinary rank must be small, and your hardness condition says that your non-negative rank with respect to all balanced partitions should be large. Okay, these are the two conditions that you absolutely must satisfy for the task that you have set yourself. And so if you found such a polynomial, this is where the connection to log rank conjecture comes in. If you found such a polynomial, then what happens is that you would have immediately refuted the log rank conjecture. Okay, why? Because here's the log rank conjecture, and this is a very good, very interesting conjecture, which is earlier Leonard Schulman was saying that it's worth wasting or ruining your life on some problems. Here's another one, which is I certainly recommend ruining your life on, which is
we have only 2 minutes.
Okay, yeah. So I can't ruin your life much, and I'll be just done very quickly. So, but the conjecture says that it's a matrix theoretic form of the conjecture, which says that you take a Boolean matrix M, and the non-negative rank of the Boolean matrix cannot be too much larger than the ordinary rank of it. In other words, at the log scale, if you take the log of both sides, the log of the non-negative rank can at most be a polynomially large in the log of the ordinary rank. And this conjecture has been wide open. We don't know how to prove or disprove this. So if I want to solve the problem if we sort of solve the problem of this depth 3 versus monotone in the usual way using Boolean polynomials, then we would have disproved the log rank conjecture, and this we have no idea. Since I have no much time, what I will say is that recently, okay, this is going to be my last slide. We sort of avoid this by going to what's called the log approximate rank conjecture, which was also posed by Lee and Scheibman. And what it now stated was that, okay, suppose your matrix is no longer Boolean, but it's an approximately Boolean matrix, meaning entry-wise, every entry of this matrix is very close to being Boolean. Okay, each entry is approximately Boolean. And then this approximate rank conjecture, which seems a much stronger form than the Boolean conjecture, is that even then, the non-negative rank should not be too much larger than the ordinary rank. This was the log approximate rank conjecture. And in a recent work with two TIFR students, Nikhil Mande and Suhail Sharif, we were able to disprove this conjecture. And what we use in our work here, in this work, is take the counterexample from this log approximate, the counterexample to the log approximate rank conjecture, and cook up a polynomial. Actually, it's this, in some sense, it's not much cooking up. It's basically once you see this framework, it's a very natural polynomial that you get out of this counterexample. And for that polynomial, it turns out there is a depth 3 circuit, and we can show that every monotone circuit will require exponential size. Okay. And okay, now I have to just skip all these slides, and yeah, let me just say there are many open problems. One is to, we got, as Ramprasad said, what is the right lower bound? I mean, the best lower bound you could show with the polynomial that we had is, as I said, 2 to the omega root n. We only were able to show 2 to the n to the 1/4. Can you improve this? I mean, can you find some monotone polynomial in constant depth? I mean, circuits with cancellations can do it in constant depth, but the monotone complexity is 2 to the omega. Yeah, this would be a fantastic result, because then it would be the strongest possible separation. This would both quantitatively and qualitatively subsume variance result. At this point, we have just qualitatively subsumed variance result. The second interesting question is, can you prove the Boolean analog of this result? Yeah. So in the Boolean world, this is wide open. We even don't know whether formulas, general formulas with cancellations are exponentially or super polynomially more powerful than monotone circuits. Okay, so this is wide open. And the other one is a bit more, I mean, can our techniques be used to prove lower bounds against more general circuits, not just monotone circuits, but set multilinear, non-commutative, multilinear, so on. Thank you. Sorry for
Thank you,
going
Arkadev.
over now.
So, does anyone has any question? We can have a quick question.
Hi, Arkadev, I have a question. Mrinal here.
Oh, hi, Mira.
So you use this decomposition theorem for monotone circuits where you write your polynomial as sum over alpha I, beta I, right?
Right.
So if let's say if you were promised that there is a stronger decomposition theorem where each of these summands, instead of having 2 factors, has many factors,
Right.
would this give a better lower bound in your framework? Or
Interesting. So we have been thinking about this question, and it's not clear how to make use of that.
so you can always reduce it to 2, right, by multiplying stuff, but that's not.
Yeah.
I meant, yeah.
I know. So you will certainly get at least the same bound, but your question is, can you improve your bound,
Right.
knowing that it comes from knowing that it has more factors, right?
Right.
Yeah. So this is like the formula kind of thing, right?
Right.
So I mean, so far we have not been able to get a handle on that, but my belief is thinking along this line, you should be able to do that.
Okay.
Yeah, you might want to go to K-party communication and so on.
Right. Okay. Thanks.
Thank you, Arkadev.
Thank you.
Let's thank the speaker again, and we'll have our next talk by Anna.
Yeah, let me stop sharing my screen.